Okay, gang, welcome to Computer Graphics. This is our last lecture before we break for Christmas, New Year's. So this will be the last time you have to listen to me talk, well, at least for a lecture, for this year, right? Last time for this year. And why is that? Because we are meeting on Friday, but remember, Friday will be your team meetings. And so what we're going to do today is I'm going to go over the programming assignment. It's already been out on Moodle for a while now, and I hope you guys have looked at it, but we're going to go through it line by line. Then I'm going to show you my solution running, and then we're going to go through a framework that I've already posted out on Moodle that's available for you guys, and you'll basically see there's stubs for everything, and you have to fill in the program stubs. And then after that, after we're through with the programming assignment, I'll entertain any questions you guys might have about the sort of sprint, if you want to use that phrase, presentations that we're going to have on Friday. Okay? So that's the plan for today. Let's see. We'll start out by, I want to start out by reminding you guys about the pyramid. Our assignment is going to deal with a pyramid, and it's actually already, we've pretty much covered this pyramid in lecture when we were describing how polygons are stored inside a computer system. And so here was a polygon. It's a pyramid. It consists of here's an object. It's a 3D object. It consists of 5 polygons. 4 of those polygons, front, back, left, and right, are triangles, and the last polygon is the base. And the vertices, I didn't give any coordinate numbers. We weren't there at that point, so I just gave them names. But obviously, each of these will have to have an X, Y, Z coordinate associated with them. But anyway, the important thing here was I wanted to show you the structure, that you have objects that consist of polygons. And those polygons generally consist of lists of points, and all of those points are the vertices that the object depends on. So there's kind of 2 things here. There is some points in space, right? We call them A1, B1, B2, B3, and B4. In reality, these would be X, Y, Z coordinates. So there are points, and then there's a structure. From the points, the first level structure up is the collection of polygons, and then the object itself is a collection of those polygons. And so when we define objects in programs, we'll have to respect a structure like this, okay? So why don't we dive into the actual program assignment? Okay, so here's our assignment. It's due the day after the day we get back. It's due on Tuesday, January 5th, okay? And it's about, what is it about? It's about 3-dimensional transformations and perspective projection, everything we've been talking about. So this is an individual assignment, so you have to work on your own. The assignment will be written in Python and use the provided tkinter framework. So it's going to use Python for the code and tkinter for the interface and for the drawing window. Specifically, you'll build a system that allows you to render, i.e. to see and move, to scale, translate, and rotate a single object. So this project has one object. It's a 3D pyramid that has a wireframe viewing system. So by wireframe, I mean that we draw the edges of it. We don't try to make it solid or anything like that at this point. It's just wireframe, which is exactly like the drawing I just showed you guys in the notes, okay? So you should do the following. Use the definition of the pyramid provided below from these, so these are the underlying points, okay? So the apex is at an x of 0, so it's lined up, right, with the y-axis, the vertical y-axis, because you're translating no distance in x. In y, it's 50, so it goes 50 up, right, because it is the apex. And then it is 100 pixels or not pixels, 100 units in positive z. Okay. Now, if you look at the base points, you've got two front base points, right, and they are a distance of 50 away from you, and you have two other base points, and they are 150 away from you. Okay. So these are the front points from the, they are the front points from the sense of the initial definition of the pyramid, and these are the back points. And it makes sense because, right, the apex is in the middle, right? So halfway between 50 and 150 is 100, right? So that's why for the z distance, you have got the front, you've got the apex that's essentially in the middle, and then you've got the back points. And then you can look for, base 1 is, over minus 50 in x, down 50 in y, and etc. So if we were to go back to our image for a second, I believe if you look at it, I actually in the program, I'm counting this as 0.1, 0.2, 0.3, and 0.4. So it's still clockwise, but I think I've shifted them by 1 in my definition. So I had intended to make them match perfectly, but it looks like as I look at the code there that I didn't quite do that. But that's fine. From these points, you should be able to build the five polygons. It's just that one is minus 50, minus 50, and actually, if the origin did like this, if the coordinate system did like this one is actually minus 50, minus 50. So again, the way I have them there, this would be 1, 2, 3, 4 is the way that I've done it in the program definition here. Okay, so given these points, right, what you need to do is you need to build a list of points that will be used by the object. So basically implement these. In the sample code, this object is called pyramid point cloud. So the vertices, the list of vertices without any information about how they're connected together or to form an object through polygons is just called the pyramid point cloud. It is the vertices that your translate, rotate, scale will work on. So this point cloud, the collection of object vertices, as I just got through saying, will be used to scale, translate, and rotate the object. Okay. You will also need to build a list of points for each polygon. So it'll pull from the pyramid point cloud, but it'll be the list of points for each polygon. So again, that is exactly what I showed here in the notes, right? Where you had a list of points that defined the front polygon, and a list of points that define the back one, and the left one, and the right one, and the base. So this is what I'm talking about in that second step, is you have to define each of your 5 polygons. So build a list of points for each of the 5 polygons. that will be these will be used to draw each of the lines making up a polygon. My grammar there's not the best. Okay, and then the third thing is build a list of polygons for the object. In the sample code, this object is called pyramid and will be used to draw each of the polygons that make up the object. So there's like there's three levels. There are the vertices, the point cloud. There are each polygon that has to be defined, and then the object is that collection of polygons. Now, obviously, if you had different objects, right, the polygons making up those objects would be different, and the point clouds for those different objects would be different. But right now, we're only having one object, the pyramid. Okay. So once you've got your object, you'll implement the code for perspective viewing of three-dimensional images. So that's the projections that we went through. We'll use a left-hand system for viewing, just like we did in our notes. Objects are going to be in positive z, and the viewer will be in minus z. The viewer is situated at 0, 0, minus d in the world coordinate system, and you will use a d of 500. So 0, 0, minus 500 is where the viewer will be. Linking that back to the notes, we talked about projection, where the center of projection is this D. That D is 500, and this point is 0, 0, minus 500 because we exist in the minus Z space in a left-hand system, and everything we're going to be playing with is in the positive Z. And here again is just more of a three-dimensional-ish. Here's the center projection. This is, again, the negative Z, and the objects are out in positive Z. We've actually flipped this one over, right, because in these drawings, we are over here on the left side, and in this more three-dimensional kind of drawing, I've changed my perspective, and here's the real world, and here's our screen that we're looking at, right? But it's the same thing. This is minus Z where the user is, where the center of projection is. We are 500 in front of the screen, so this point is 0, 0, minus 500. Okay. Oh, let's see. Okay, so that's the perspective projection code. Implement the code for conversion to display coordinates. In tkinter, the origin is in the upper left-hand corner of the window. So before you can actually draw a line on the canvas, the projected points must be modified to display coordinates. What you must do is mathematically move the origin from the upper left-hand corner to the center of the drawing canvas and then flip the y-axis because it is down instead of up. We went through all of that carefully as well in the notes. That was the next thing we talked about when we had this, and the notes have a drawing system that is exactly like the drawing system in tkinter. So the equations that I gave you are exactly the equations that you'll need to use to do the conversion. Okay, see how simple I've made things for you guys? I've made everything match up for you. So let's see. Okay, so first you define the vertices, and then you define the object as a collection of polygons. And once you've done that, you ought to be able to project the objects onto the screen, to project the objects into 2 dimensions, and then convert those into the coordinate system used by tkinter. Okay? And then you need to do the implementation of all of the things that we talked about. Implement the code for uniform 3D scaling. By uniform, I mean we'll scale equally in all directions. Implement the code for 3D translation along each of the primary axes, X, Y, and Z. Really what you're going to do is you're going to have a single equation that does translation for any arbitrary vector, but your interface will restrict you to moving along X, Y, and Z. Implement rotation along each primary axis, X, Y, and Z. Notice that these rotations, there should be an S there, will not be in place rotations. Instead, the rotations will be defined with respect to the world coordinate system. And we've talked about this. So if your object is centered, the rotations will appear to be in place. The object will not move. But if they're not, then the object will appear to move. You also need a reset function that'll reset the pyramid to its original location. And I like that because after we've messed with it for a while, it's kind of hard to see some things, so we can just reset it to where it was to begin with. And so if I'm like looking at your rotations, I know what I expect them to look like for the object where it's initially defined at. So it just makes it easier to grade, and it makes it a little bit easier to debug if you can pop back to the original location. So there's a reset button. And then you're going to build a GUI. Actually, I'm building a GUI and I'm giving it to you. Additional requirements, you've got to work independently. It's got to be your own code. You must thoroughly document your program. This includes comments at the beginning of your program with your name, your student number, the date, the assignment number, and a brief description of what the program does. I always have some gimme points in the programming assignment, and documentation are the gimme points. If you do this, you'll get like, I don't know, I have to look at the grading rubric, but I think it's 10. I think it's a letter grade. I think it's 10 points. So you can get 10 points just by putting a comment block at the top of your program with your name, your student number, the date, the assignment number, and a brief description of what the program does, as well as sprinkle some comments throughout the program. But really, I've already commented, sprinkled comments throughout the code that I'm going to give you. So the second part's, at least part of it's already done. The flip side is that if you don't put in exactly what I asked for here, I take a letter grade off your program. There's always, 10 or 15% of the students who forget to put the comment block at the top. And I'm like, guys or girls, it's like I went over it and I said, just do this and you'll get 10 points. But if you don't do it, I'll take off the letter grade. So please remember to put your comment block at the top. When I look at your code, it's one of the first things I look at. Did they follow those directions and do that? It's a good habit to have a comment block at the top of your program that identifies who you are and what class you're doing it for, blah, blah, blah. So this is a good habit to get into. I just insist that you do it, okay? Your program must be written in Python. It's got to run in Thonny. I don't care what you use as your IDE, but I don't program very often, and Thonny is a cute little IDE for beginners, and I'm a beginner. So I like a nice little simple IDE because I don't program enough to need something big and fancy. And then it's just, oh, how do I compile the damn thing, right? Well, in Thonny, you hit the little button and it's fine. So, I like a simple little interface. So, your program, if you give me a Python file, right, Thonny ought to run it. It might not be a bad idea just to download Thonny before you turn it in to me, check and make sure that it'll run in Thonny. Shouldn't be a problem, but it is. Don't use any built-in graphics functions above the line draw level. That is very, very, very important. You are building the graphics system, okay? The only tool that I'm giving you is a Thonny canvas and the permission to use line draw. Don't use anything else, okay? Don't use the NumPy library, for example, to do any of the calculations. You're supposed to do those manually by hand using the formulas that I've given you, okay? Submitting your assignment for a grade. Every one of you are going to have to meet for me for 15 minutes on January 5th to demo your program and explain how it works. To make things fair, the programs, everybody's program is due no later than 8 a.m. on Tuesday. And when you start to run your program, one of the things that I'm going to ask is, okay, show me the timestamp on the file you're about to run. This is the only fair way we can do things, because if you have a 3:30 in the afternoon appointment to meet with me and somebody else has a 10 o'clock in the morning appointment to meet with me, you know, you shouldn't get an extra, 5.5 hours to work on your program. So, so you have to run the code that you turned in, and we will look at the timestamp to make sure of that. Now, very important, that means don't screw around with your programs after you've turned it in. If you want to continue to play with your program, fine, but make a separate copy and work on that separate copy, because it's unfortunate when I ask to look at the code and the timestamp, and it's 12:30 in the afternoon and the program was due at 8. That's the timestamp. And I went, wait, that timestamp's after. And they go, oh, well, I did open. Oh, I changed. I had a misspelled word in one of my comments and I changed it. No, don't do that, because then I've got to go and I've got to try to compare the code you turned in with the code we're running, and it's a giant disaster and eats up your entire 15 minutes of our meeting. So if you're going to make any changes, you need to make a separate copy after you've turned it in so that you can show me exactly the unedited copy that you turned in. I will ask to see the timestamp. Does that make sense? Does that make sense? Yes, no, maybe, sort of. Please say yes. Okay. Are the trig functions in the math library? The trig functions are in the math library, the standard math library. They're not really in NumPy. So yes, you can use trig functions. You can, but the trig functions expect radians, and we're going to be doing things in degrees, but there's a function in the math library to convert degrees to radians. So you'll have to remember to do that conversion. So if we're moving something by 5 degrees, that's 5 degrees. That's not 5 in radians, okay? Let's see. How are you going to turn the program in? You're going to email them to mike@latech.edu. Again, no later than 8 a.m. on Tuesday, January 5th. It will be very important that your subject line reads CSC space 470 space colon space assignment space 1 space colon space your name. And that's not Chevron, your name. Chevron, that is your name. So, for example, if Luke Skywalker was in the class, it would be CSC470 colon assignment 1 colon Luke Skywalker. And so, why am I such a stickler on the subject line? Because I get tons and tons and tons of email, and when we go to grade these things, I need to be able to find your assignment quickly. And if we all use the same naming convention for the subject lines, it's going to be very, very easy for me to grab your program. If you give it some other name, it's not going to be, and then we'll waste part of your 15 minutes trying to find your program. And you don't need to be wasting that time, because that's time that you're not having to explain to me how your code works and for me to make sure that you really wrote your own program. There's going to be some sort of a sign-up sheet. I'll have a link on Moodle to the sign-up sheet. The sign-up sheet's going to be on Google Docs, but there'll be a sign-up sheet where you'll sign up for appointments on that Tuesday. I will have that up no later than Monday. I may try to get it before we break for classes on Friday. I may try to get it up, or maybe I'll put it up over the break. But either way, I'll send out an email when the sign-up sheet goes up to let you guys know that it's out there. If you've got a tight schedule on Tuesdays, you will probably want to try to get your name in a slot as rapidly as possible, because if you wait, you're just going to have to take what no one else wanted as far as time. And if you don't have Tuesday, Thursday classes, that's fine. But if you've got a lot of Tuesday, Thursday classes, you may find that you're going to have a problem. You have to skip a class or something. That always sucks. Of course, with all the classes pretty much being recorded or whatever because of COVID, you could always pick up a lecture that you missed that way, I suppose. But it's not good. If you've got a lot of constraints on your schedule, you should go early. Okay, did all of that make sense? Are there any questions about the assignment? So yes, you can use trig functions. Yes, those trig functions expect radians, but yes, there's a conversion routine that'll convert degrees to radians. Questions? No questions. That's interesting. No questions for Mikey. Okay. Well, there is a question here. So we have to make sure to calculate the points, but we will use line draw to connect them. That is exactly correct, Logan. Completely exactly correct. Can everybody see my funny, my program running? Can anyone see my program? Okay, all right. Okay, so this is the program. Here we've got a drawing window. I made this drawing window 400 by 400. It's not a huge window. Don't go over 800 by 800 or we might have trouble on some displays. Remember, I tend to make my displays big because my eyesight is poor. If you make your drawing window too big, your buttons will be off the bottom of the screen. That'll be a problem for us trying to run it. So I made this 400 by 400. You could make it 600 by 600 if you wanted to, maybe 800 by 800, but don't go any bigger than that. And yeah, I made it square. It doesn't have to be square. It can be rectangular if you wanted it to be, but that was just the decision that I made. Okay, so we've got a pyramid here, and you can see we've got some controls. They fall into 4 boxes: the reset controls, the scaling controls, the translation controls, and the rotation controls. These things are called labels here. Okay. And within the groupings, like within the reset panel, there is a reset button, and I made the text on that green. Now, if I hit reset right now, it doesn't seem to do anything because the pyramid's already in its natural original position. But I can scale it. I can make it larger by pressing the button multiple times, or I can make it smaller. Again, I'm pressing the button multiple times. But by doing that, we get a kind of an animation, right? It's not 144 frame per second animation because I can't click the button 144 times in a second. And the program wouldn't be able to redraw it either. But that gives you an idea, larger and smaller, larger and smaller. If I reset, it goes back to its normal position. Now, we can translate forward and backwards. Forward pushes the object into positive z, which is away from us, and in fact makes the object look like it's growing smaller. It's growing smaller not because the object is getting smaller, but because we are pushing it further and further into the distance. We are pushing it further and further into positive z, and we are located at minus 500 in z, so it's getting further and further away. I can do the opposite, and I can move it backwards. Backwards means that I'm pulling it towards me, right? And it gets larger, apparently, because it's actually getting closer. So forward and backward look a lot like smaller and larger, but they are different things. One of them is changing the actual size. Scaling is changing the actual size of the object. Forward and backwards are moving the object, but because we're using perspective projection, when the object moves closer to you, it looks bigger, and when the object moves further away, it looks smaller. Also notice that we talked about the fact that the distortion increases the closer something gets. So the distortion of the front versus back, the ratio of the difference between the front and the back gets more pronounced the closer the pyramid gets, because relatively there's a lot of difference between the front and the back here. The smaller triangle is the back, this bigger one is the front. So if this were a solid, we wouldn't see this line or this line or this line or this line or this line. All you would see would be the front-facing triangle. That's all you would see in this case. Now, you can also translate to the left, to the left, to the left, to the right, to the right, to the right. That would have been funny about, 10 years ago. The Boot Scootin' Boogie was a popular song. To the left, to the left, to the left. I know it's sometimes taxing. I have to put up with my dad humor during these lectures, and I do sincerely apologize for that. Okay. And you can translate up, and you can translate down. Okay. And you can always reset. So those are the translations. Now, remember, if we go back to the assignment, it says something like, let's see, it says, it said, implement code for 3D translation along each of the three primary axes, X, Y, and Z. And I said verbally, well, really what you're going to do is you're going to implement a single translation function that can translate along any three-dimensional vector. And then I said, but the interface will restrict you to X, Y, and Z. So that's what I'm really illustrating here, is that the interface is what is, this is the, right, forward and backwards, that's Z, left and right, that's X, and up and down, that's Y. So you can either move some fixed amount, right, in Y. So that's a vector that's like 0 minus 5, 0 is like what this vector is. And this vector is like, it's the X, right, if we're going positive. So it's like 5, 0, 0 here. But these are just feeding different vectors into a single translate formula that could taking any arbitrary three-dimensional vector. Okay? All right, let's reset one more time, and let's look at the rotations. Well, the first thing is we don't draw the axes, but the axes would actually cross. The origin point visually would be right there in the middle of the pyramid. So the pyramid is drawn so that it is centered along the z-axis. How do I say this? When viewed along the z-axis, the visual center of the object is at the origin. So because of that, if we translate around z, the object is being translated in place. I am translating it in z, but since it's visually centered at the origin, the object doesn't appear to be displaced in any way. Okay, if that makes sense. Okay. So z-axis rotation works as if it's in place. Now, when we did the scaling, when I illustrated that, right, I had the object in its default position where, again, the center of that object, the visual center of that object is where the center is. But let me say that I take this object now and let's move it to the right. We'll skip the song here, right? And up. Now notice how our perspective is changing here, right? You know, this edge isn't nearly at the same angle as this edge. Why? Well, because we're staring. Always remember that your eye is looking at this point right here. So this is getting closer to your peripheral vision as it moves. Oops, well, that was the edge of what I'm drawing there. As it's moving to the side of your vision, and that's why the distortion increases the further it gets away from the spot that you're looking at. Does that make sense? So let's take this object. Let me move it back left just a little bit. So now then, this object is no longer centered right at the origin. I've moved it to the left and up a little bit. So now if I scale larger, you'll notice, keep your eye on this point here. It's moving, right? You can definitely see that the object is moving. And if I go smaller, right, you can see how the thing is moving in space. But again, if I reset, it's no longer. Well, you can say, yeah, it's moving in space, but it's not. It doesn't seem to physically move. Its XY location. Okay. And again, if I move it, let's keep it kind of tiny and move it up and to the right quite a bit. If I then go larger, you can again keep your eye here, and you can see that it's moving, right? So it's not. It's scaling, but it's still scaling relative to the origin. Does that make sense? Okay. All right, so we've looked at everything except X and Y rotation. I've saved those to last. So if we think about the Y axis, the up and down axis, it is at Z equals 0 is where this pole would be, but my pyramid is not at z equals 0. My pyramid is actually, the front of it is at plus 50 and the back of it is at plus 150. So if the y-axis is here, right, your pyramid's is over here. Well, I can reverse it, is over here. Okay, so when I rotate it around the y-axis, it's going to dance around that y-axis like this. It is not going to spin in place. So when I rotate around the y-axis, it's not going to spin in place. It's going to spin around the y-axis, and we can see that. It is, you think of a pole, right? That's the y-axis, and it's doing the right thing. It's dancing around that pole. Oh my goodness, I'm saying this pyramid's pole dancing, but it's rotating around that pole that we can imagine, that vertical pole that we can imagine, and it can rotate in one direction, and then you can make it rotate in the other direction. Do you see what I'm saying? And when I am rotating, but I'm rotating around the y-axis, and this pyramid is not centered on the y-axis. If it had been centered on the y-axis, then it would spin in place, but it's not spinning in place. It's rotating around the y-axis. Okay, X is going to work in the same kind of way. The x-axis is like a horizontal bar, right? But that horizontal bar is in front of this pyramid. So I'm going to rotate it around that horizontal bar, and it's going to move around the bar. And when you take these images and they're still, it sometimes becomes hard to tell what's the front and what's the back. But if you start to get confused, if you do what I'm doing here, which is, you know, by hitting the button over and over, animate it, you can, your eye will catch what's the front and what's the back because of the way it's moving. Okay. We will, when we get to hidden surface removal, the thing will look a lot more, quote, solid, and you can do it in the opposite direction as well. But this is proper behavior because it is rotating around the x-axis. Okay. Questions? Okay. So now everybody should have a good idea in their head of what their program needs to do when it's running right. That was the whole point of going through this. So you now, there should be nothing unexpected that happens. You now know what the program is supposed to do, okay? What it looks like when it's running properly. So let's go and look at, let's not look at the solution. Let's look at the framework. So here is the program framework. It does not have a comment block at the top. Please remember to add your comment block at the top or you will lose, I've forgotten, it's 10 points or 20 points, but you will lose a bunch of points if you don't put the comment block at the top. So I'm using the math library. Again, I'm not using the NumPy library, I'm using the math library. Report to Kinter. I told you that I used 400 and 400. You could use up to 800 to 800. Don't get bigger than that or your controls might slide off the bottom of my computer. What's our D? Our D is 500, all right? Now remember, we're going to be at 0, 0 minus D. So we will be sitting at minus 500, but the distance from your virtual eyeball to the virtual screen is 500 units, whatever units that is. And here is the apex of the pyramid and the 4 base points, the 5 underlying points. Here is how I defined the 5 polygons, and they are defined clockwise for the front, the right, the back, the left, and the bottom, or they should be if I didn't beef up anything in the way I numbered these. There could be an error in my ordering because, again, we're not really using order right now. So now that I found out that I actually numbered the base points differently, I need to go back and check to make sure that these really are in counterclockwise order when viewed from the out, or in clockwise order when viewed from the outside. I know the base is right. I need to go back and recheck my my front and right and back polys to make sure they're okay. Because if I'm looking at this, I'm actually thinking that what I'm calling front poly is actually the left poly. Anyway, these are the polygons. These are the points, and we've defined the points up here. What's my object look like? It's a pyramid, and the pyramid has 5 polygons in it. I'm just making a little note to myself to check the polygon order. If I find that it's goofed, I may update it here. Again, it's not going to make any difference for this programming assignment whatsoever, but later programming assignments, if you don't have the orientation of the polygons defined correctly, starting with assignment 3, it'll make a big difference. Okay. Okay, polygon reset. Now, what happens if we run this framework? Well, actually, you'll see that the framework is actually runnable. If I can get to my controls. Let's see. So what will the thing do if you run it? Well, if you run it, you see that there's no object, but you can press all of the buttons, and though you cannot see, every time I press a button, I get, let me share the other thing. Every time I press a button, I get a message that gets printed out. So like I'm pressing the smaller button, and you can see scale stub executed because I'm scaling. This is a reset pyramid stub executed, and then draw the object. If I hit a rotate, it says rotate Z stub executed. If I hit -Z, it says, it still says rotate Z stub because that was a Z that I did. So these stubs just exist so that you can see that that clicking the button does something. Those print statements are supposed to be deleted when you actually write the code that goes in the stub. But I found students from previous quarters left in their stubs, their print statements for their stubs. Don't do that. It's just there as a little debug thing to let you know, oh, when I hit this button, this piece of code gets executed, right? It's not supposed to be there in the end. It's not in my program when I run it. Instead, the code that resets the pyramid is in the reset pyramid function rather than a print statement that says, oh, the reset pyramid stub was executed. It won't be a stub anymore after you filled it in, right? Am I making sense? So yeah, please keep that in mind. Okay, so that's the reset. Then it's like, okay, this function translates an object by some displacement. The displacement is a 3D vector, so the amount of displacement in each dimension can vary. So define the function translate, it takes in an object and it takes in a displacement. And the displacement is a three-dimensional vector, and it does the translation. You'll have something similar for scale. This function performs a simple uniform scale of an object, assuming the object is centered at the origin. The scale factor is a scalar, so object and the scale factor are the inputs there. Rotate around z. This function performs a rotation of an object about the z-axis from plus x to plus y by some number of degrees, assuming the object is centered on the origin. The rotation is counterclockwise in the left-hand viewing system when viewed from minus z, which is exactly the way that I set up the equations that I gave you in the notes. Here's the y rotation. Same thing. Use the equations I gave you for y rotation. Here's the x rotation. Use the equations I gave you for x rotation. This function will draw an object by repeatedly calling draw poly on each polygon in the object. So if I want to draw an object like a pyramid, it's going to call draw poly for each poly that's in the pyramid object. So there are five polygons in the list that is the pyramid object. So it would repeatedly call draw poly 5 times, one for each of the polygons. So what's draw poly? Well, draw poly is a function that repeatedly calls draw line for each pair of points that make up the object. Remember to draw a line from the last point to the first point. And so draw poly is using draw line, and draw line we'll use the statement. I've commented it out to give you an idea. W create line from in display coordinates, the start display coordinate in X, the start display coordinate in Y, to the end display coordinate in X, to the end display coordinate in Y. So you've got to give 2 points. Each point has an X and a Y, and that's what you need to give into the create line. So that's the draw line function that you're allowed to use. And I commented it, but it's an example of how you draw a line in Tkinter. Okay. Now, this uses coordinates that are in display, points that are in display coordinates. This function will convert from 3D to 2D using perspective projection. And note it will return a new list of points. It will not keep, we don't want to keep the projected points of our object around. So this does the projection, and it's going to return PS, which is going to be the projected point. You give it a point, it returns a prospective projected point. Okay, and then convert to display coordinates. We'll take in a point that's been projected, right, and then it will return that same point having been converted to the XY of the display coordinates. So you're going to really draw, display coordinates when you call, your line draw here. Okay. Everything else below this is the interface, and we'll talk about that in a minute, but I wanted to go back here and make one very important point. Now, I know all of you use Python, and you're familiar with how Python works. But a very important thing, when you are resetting your pyramid, in fact, when you're changing any of the points, you have to be very careful, because what I built here is a structure where polygon, right, where pyramid is a list, right, of pointers to polygons. A pyramid object is a list of pointers to polygons, like bottom poly, front poly, etc. And each of those polygons is a list of pointers to actual points. So apex here, 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 and here is not a copy of the apex point. It's a pointer to apex that's defined in one position here, in one place. And so if you were to say something like, apex equals some new point, you just destroyed the pointers that you had, because it's no longer, apex will no longer be pointing to this location here. You will have changed it. And so you can't just, when you're resetting the pyramid, you have to go down into the pyramid point cloud list and change the values. You guys should know how Python works. You guys should know the difference between a value and a pointer. But what I'm saying is about half of the students who do this thing, not half of the students who get stuck somehow, they're stuck because they say, well, I keep changing this, but it's not changing. Well, that's because you created a new thing that you're playing with, and your old structure that you're using to point into things, you haven't changed it, right? So that's something to keep in mind as you play with these things. So if you're making changes and nothing's actually changing, right, and you're confused, probably what you did is you created a new object, and your old pointers in your for your pyramid and its individual polygons are not pointing at the new thing that you created, is probably what's happening. Okay, so what does the interface look like? The rest of the stuff is just how we use things. So these are functions that are called by the interface. So like if we go back to the interface, we have things like reset, larger, smaller, forward, backwards. These things are these things like larger and smaller and reset. These buttons are directly calling the functions that I'm now going through. So this is part of the interface. The buttons, I'm going over the callbacks to the buttons in the interface now. Okay? So let's look at these callback functions. So when you press, Michael. When you press the reset button, what it does is it deletes all. So that gets rid of all of the drawing. Then it calls the reset pyramid function, which we define upstream. And then it calls the draw object pyramid, because we only have one object to draw. When you hit larger, you delete everything on the screen. You call the scale function with the pyramid point cloud, and 1.1 is your scale factor. So that'll make it grow larger by 1/10. So every time you hit the button, the larger button, it calls this this callback function, which clears the screen and scales the polygon to be 1/10 larger than it was, and then calls the draw object on the pyramid so you can see the thing. And every one of the callbacks works similarly, smaller. Erase everything called scale with a 0.9. That'll cause it to get 10% smaller. Now redraw it, because otherwise you wouldn't see it. When you move forward, clear the screen, translate the pyramid. This is forward now, so it's away from you and Z, so it's positive Z. So don't change the X, don't change the Y, multiply the Z by 5, or add 5 to it, because this is translate, right? So this is the vector. It's just that when you click forward, that moves it away from you in Z by 5. So when you click the backwards, it moves it closer to you by 5. When you click left, it changes your X by -5. When you click right, it changes your X by +5. When you click up, it adds a 5 to your Y value to move you up. When you click down, it subtracts 5 from your Y value to move all your points down. X plus and X minus, these are the rotations around the X-axis. So if you go plus X, it rotates it 5 degrees. Remember, this is in degrees around X. If you rotate, if you hit X minus, you go -5 degrees in X. If you click Y plus or Y minus, same sort of thing, 5 or -5. And then if you do it for Z, same sort of thing, plus Z. Clear everything off, rotate by 5 degrees in Z, and then redraw the pyramid. Z minus, wipe everything off the screen, rotate by -5, redraw the pyramid. Okay, so that's all of our callback functions. So now we've got to build the interface that calls those callback functions, the interface with the buttons. So root equals tkinter. We've got an outer frame, which is our root, and then pack, that just kind of does a cleanup thing. We've got a canvas, right? It's got some canvas width and some canvas height. This is the 400 that I defined right at the top of the program. You're going to want to draw your pyramid to begin with, and then pack to start, so you can see your pyramid when you begin. You got a control panel. That's the outer, it fits in the outer frame. And then you've got reset controls is one of the little, so within the control panel, which is this whole thing here, right? You've got the reset frame and the scale frame and the translation frame and the rotation frame, and each of them will have a label that tells you what it is, and then within there you're going to have buttons that are going to have labels. So we're building all of that here. So reset controls, it's to the left side of the screen. You're going to put a label on it that says reset. You're then going to have a reset button that says reset. Its color of that button, the foreground color for the text is actually green in that case. And what does it do? It calls reset. It calls the reset callback function. So that's how, when you press the button that says the word reset on it, it calls the reset callback that we just talked about. And then you got scale controls, and there's going to be a label that says scale, and there are going to be two buttons, the larger button and the smaller button. The larger button says larger, the smaller button says smaller. When you press larger, it'll call the larger callback. When you press smaller, it'll call the smaller callback. Then there's the translate controls that moves you, that moves things, right? So you're going to have translate controls. It's going to be a translate label called translation, and then you're going to be able to move forward, backwards, left, right, up, down. Click the forward. These are buttons. You click the forward button, it calls forward. This is a button called BK. You click the Burger King button, the back button, and it calls backward. Call back, and left, right, up, down works exactly the same. Finally, we've got our rotation control panel. It's got a label that says rotation, and then it's got your well, X plus, X minus, Y plus, Y minus, Z plus, Z minus, and it's got these little, this is what's written on the buttons. If you click X plus, it's going to call the X plus callback, minus X minus callback, etc. Those are the names, are all the callback functions that it's calling. When you click the button, and then root.main loop, because this is a GUI-oriented program, and so you're not writing a main program. The main program is running the interface, and you're just writing callbacks. Questions. We went through a lot of ground there. Questions. Questions. I expect there to be questions. You can type them or you can ask them. No questions from Eric. Questions. I went over this. I mean, we took pretty much the whole class to go through it, but I think that things should be pretty clear. Should we not modify the buttons at all? Andrew, everything below the line in the code where I said this is the interface, you guys don't need to change a word of that. Because it already works, and I showed you that really what you do is the functions that have the stubs that have, this is the so-and-so stub, you take out the print statement and you add the code there, okay? Let's see, I get that we don't need to, but if we add a button to make it do the Cupid shuffle, will that affect the grade? Here's what I always recommend. That's a good question. Here's what I always recommend. Do what I asked for, save that off and submit it, and then when we are meeting, if you've added additional features, I find it fun for you to go through that with me. Will it affect the grade? No, both for better and for worse. So if you want to play around with something because just are having fun with it and want to add it, I'd like to see that. But to make sure that everybody's graded fairly, I would ask that you write something that conforms directly to to what was asked for. Okay, which does not require you to change the interface at all. And so that way I've got the same thing to grade that I got from everybody else. And then if you've got something else you want to show me that you played with, that's great. And I'd love to see it. The reason why I do it like this is sometimes students get so excited about implementing something new and different that they skip over something that was asked for in the actual assignment. And that's problematic. I hate giving somebody a lower grade even though they did more work. And so the best way of separating that is I say, give me what I asked for, that's what we'll grade. And then if you've got something cool for me to look at, we added an animation or something like that, I'd love to see it. Okay? Other questions? Okay. All right, so how about questions about the project presentations for Friday? We still have a few minutes to answer any of those you might have. Remember, on Friday, you guys are going to be doing the work. Now, I haven't, are y'all planning on having your whole teams meet together and running, one Zoom, that you connect into the class with, or are each of you planning on running your separate Zooms, and maybe you're not in the same location and you're handing off different parts of the presentation from one another? I need to know that. If you are going to need screen sharing capability, and I assume at least, well, to keep things simple, let's say that we keep screen sharing to only one person in the group. That'll keep things simpler for me. But you'll need to tell me okay, who needs to be, who's going to screen share so I can give them moderator privileges so they can share their screen, because by default you guys aren't allowed to share screen. So I would encourage people maybe to show up to class early. I use the same Zoom room for my office hours as I do for this class, and say I'm supposed to be in by 10 o'clock, but I'm frequently not. But I'll make an effort to make sure that I'm in the Zoom room, say by 10:30 on Friday. So if you need to do any setup ahead of time, you know you're going to need moderator privileges or something like that. I can go ahead and give them to you before we get started. That might make it a little smoother. Can you pin a screen share so it doesn't change depending on who is speaking? I think it does that by default too, Eric. I did the senior capstones as a big group meeting in the spring, and I don't remember doing anything special. And I did review the recording, and in the recording, the speaker in the recording was the one that had the larger share of the video screen. So I think if nothing else, if you put it on, you know, if your view is by speaker or whatever, you'll see the screen of whoever's speaking, and if that's the person who's doing the screen sharing, then that'll work. Yeah, Andrew, like I said, that's all you need to do is there's a big button that says share screen at the bottom that I press when I want to share a screen, and I've got mine set up so that I select which window I want to share, so I'm not actually sharing my entire screen, which is cluttered and messy. So that's the way you do that, but you can't do that unless I give you privilege to do that. And so I have to make you a moderator or co-moderator, whatever it's called. But we can do that. That's why I'm encouraging, if you're responsible for making sure your team's presentation works right, I encourage you to show up early so we can work these bugs out of things. What kind of things do I expect to see and be addressed on Friday? It's like a sprint. I want you to, what are you guys doing? Okay. And how much progress have you made? And those are my main questions. What are you doing? And how much progress have you made? You might have a little demo to show, but it's early, so you may not have a demo to show. You may have a screenshot of something that you've worked out that's representative of what you're going to show. Or maybe you have screenshots that exist of assets that you include that you intend to include in your program. Those are things. I do expect everybody on the team to tell me what they're doing, so everybody needs to speak. It's just a stand-up. It's like 10 minutes where you where you're given a progress report to me and everyone else in the class on what you're doing, what tools you're using, and how much progress you've made. I expect there to be questions from the audience. If you see something that a team is using and you would like to learn more about it, you should ask them, oh, that's really cool. Where did you get those assets? Or are you guys using Maya for modeling? Or, that sort of thing. So it's kind of an information. It's the key. We're doing these things to make sure that you guys have quick deadlines, to make sure that you're working on the project as we go through the quarter. Because otherwise, everybody would put it off to the end, and that would be terrible. So I want to make sure you're working on these things all quarter long, and I'd like to use them as ways for teams to share information with other teams. if that makes sense. Okay, so there's not a specific grade associated with your walkthrough. There will be specific grades for the midterm presentation and for the final presentation, but these are just like stand-ups. You know, if we were using you know, Agile and Scrum, which is basically what you guys are supposed to be doing. Other questions? I see that we've run a few minutes over time. Okay, gang, I will see you guys on Friday. I may go ahead and record the Friday lecture just so it's there for you guys to review, because you might find it helpful to be able to go back and review your team's presentation and see what you would do differently. I look over these lectures myself and say, Mike, you shouldn't tilt your head so much like that because it looks kind of funny. But anyway, I'm going to end the recording now. If anybody has any final questions they'd like to ask, I'd be happy to hang around and answer them. But if not, until Friday. Take care. Bye-bye.